Something hit Earth over the Arctic Ocean in February 2025, and the government satellites that track ballistic missile launches picked it up. It was moving at roughly 59 kilometers per second. The solar system's escape velocity at Earth's distance is about 42 kilometers per second. If that velocity estimate is correct, the object was moving too fast to be gravitationally bound to the Sun. And it may not be the only one. Researchers have estimated that millions of interstellar objects could be passing through the region inside Earth's orbit at any given time. Not beyond Neptune. Not hidden in some distant corner of the solar system. Potentially inside the same region of space where Earth travels around the Sun. For most of human history, we had never confirmed a single object from another star system passing through our solar system. Then everything changed. In 2017, Oumuamua appeared. It was strange, fast, and unlike anything astronomers had seen before. Its unusual shape and small unexplained acceleration triggered years of debate. Then, in 2019, another visitor arrived. 2I, Borisov looked much more like a conventional comet. It had a visible coma and behaved in ways scientists expected from an icy body. 2 confirmed interstellar objects in just 2 years after humanity had seen none. Then came 3I, Atlas. In July 2025, astronomers detected a faint moving object that was soon recognized as an interstellar comet. Its trajectory showed that it had not originated in our solar system. But 3I, Atlas was different. It was moving extraordinarily fast, reaching roughly 130,000 miles per hour relative to the Sun. And its journey may have begun billions of years ago, potentially before Earth itself existed. That means this object could have been traveling through the galaxy long before our planet formed. Then came the size estimates. Observations from the Hubble Space Telescope suggested that the nucleus could be significantly larger than Oumuamua, although the exact size remained uncertain because the surrounding coma made direct measurement difficult. That immediately raised an important scientific question. If large interstellar objects are common, why did we detect smaller objects first? Astronomers expected smaller bodies to vastly outnumber larger ones. Finding a comparatively large interstellar visitor so early could mean our assumptions about the population of interstellar objects are incomplete. So telescopes around the world turned toward 3I, Atlas. The James Webb Space Telescope observed it. Hubble observed it. Ground-based observatories tracked it. Radio telescopes listened for unusual signals. And every new observation added another piece to the puzzle. One of the most interesting discoveries involved its chemistry. Astronomers measured the ratio of deuterium to ordinary hydrogen in material associated with the comet. Deuterium is a heavier form of hydrogen, and its abundance can preserve information about the environment in which icy material formed. The measurements suggested that 3I, Atlas contains unusually deuterium-rich material compared with many comets in our solar system. Its carbon isotope chemistry also attracted attention. These measurements do not mean the object violates physics. They mean that the environment where it formed may have been substantially different from the environment that produced the bodies we know in our own solar system. Then came another major result from the James Webb Space Telescope. Webb detected methane associated with 3I, Atlas. That was particularly interesting because methane had not previously been directly identified in an interstellar object in this way. The observations showed that its chemical composition is not simply a copy of the comets we know from our own solar system. This is exactly why interstellar objects are so valuable. They are natural samples from other planetary systems. We cannot travel to another star system and collect a comet. But occasionally, another star system sends a piece of itself to us. Then astronomers asked a different question. Could 3I ATLAS be artificial? Radio telescopes searched for narrowband signals that might indicate technological activity. Observations found no credible radio techno signature. The SETI Institute also conducted searches. Again, no confirmed signal was detected. That does not prove what 3I Atlas is. It simply means that astronomers have found no evidence that it is transmitting an artificial radio signal. The safest scientific conclusion remains that 3I Atlas is an interstellar comet. But the larger mystery is even more interesting. Because while astronomers were studying 3I Atlas, researchers were also trying to estimate how many smaller interstellar objects could be passing through our solar system completely unnoticed. One approach used observations of extremely fast meteors detected by sensors associated with U.S. government monitoring systems. Some of these systems are designed to detect powerful atmospheric events, including signals produced by missile launches and other high-energy phenomena. The resulting fireball data can reveal the speed and trajectory of objects entering Earth's atmosphere. Researchers searched for meteors moving faster than the solar system's escape velocity. If an object is moving fast enough, its trajectory can indicate that it came from outside the Sun's gravitationally bound population. Only a very small number of candidate events have been identified. But even a handful of possible interstellar meteors can be used to estimate how many objects might exist in the surrounding volume of space. One estimate suggested that there could be tens of millions of meter-scale interstellar objects inside Earth's orbit at any given time. That number is an estimate, not a direct census. And that distinction matters. We have not photographed 35 million objects. We have not tracked them individually. The number comes from statistical calculations based on a very small sample of candidate events. But if the underlying assumptions are correct, the implication is enormous. The solar system may be filled with objects that originated around other stars. Most are simply too small, too dark, or too distant for our current telescopes to detect. And some may occasionally collide with Earth's atmosphere. They would appear as brief flashes of light. A few seconds of fire. A signal recorded by sensors. Then they would be gone. Until recently, we had almost no way to identify which of those objects came from outside our solar system. That is beginning to change. The Vera C. Rubin Observatory is now transforming the way we monitor the sky. Its enormous 3.2 gigapixel camera is designed to repeatedly image huge portions of the southern sky. Instead of producing a single snapshot of the universe, Rubin will create an enormous time-lapse of the changing sky. Asteroids, comets, supernovae, variable stars, and potentially interstellar objects. The exact number of interstellar visitors Rubin will discover remains uncertain. Current estimates range from only a handful to potentially dozens over the course of its survey. And that uncertainty tells us something important. We still have very little data. 3 confirmed interstellar objects are not enough to determine how common these visitors really are. The next decade could completely change that. Imagine detecting another interstellar object months before it reaches the Sun. This time, we could have years to prepare. We could calculate its trajectory, study its chemistry, search for signs of activity, and potentially design a spacecraft mission to intercept it. That is the idea behind proposals for future interstellar object interceptors. Instead of watching a visitor disappear into deep space, we could send a spacecraft toward it. A close-up camera could reveal its surface. Spectrometers could analyze its gas and dust. Other instruments could search for organic molecules and other chemical signatures. We would finally have something far better than a distant telescope observation. We would have a physical encounter with material from another planetary system. And that could tell us how different, or how similar, other planetary systems really are. There is another fact that puts all of this into perspective. Every spacecraft humanity has sent toward interstellar space is traveling far slower than many naturally occurring interstellar objects. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, New Horizons. These machines represent some of the greatest engineering achievements in human history. Yet objects naturally ejected from other star systems can cross our cosmic neighborhood at enormous speeds. We have spent decades learning how to leave our own solar system. Meanwhile, pieces of other solar systems have been crossing ours all along. The difference is that now, for the first time, our instruments are becoming sensitive enough to notice. 3I, Atlas came through our solar system. We watched it. We measured its chemistry. We listened for radio signals. And eventually, it will continue back into interstellar space. We may never know exactly which star system created it. But we now know something far more important. Our solar system is not isolated. It is not a sealed bubble floating through empty space. It is part of a galaxy filled with worlds, debris, comets, asteroids, and planetary material moving between stars. And somewhere out there, another interstellar object is already traveling toward us. We just haven't seen it yet. The next one could be smaller. It could be larger. It could have completely different chemistry. And with the new generation of telescopes watching the sky, we may not have to wait another decade to find out. The solar system was never alone. We simply didn't have the eyes to see it.